So in the previous video, we talked about the idea of sketching these stretched or compressed and translated graphs. And in the end, we came up with a sense of what the graphs look like, but they weren't terribly accurate. That method is really good if you need to graph something quickly or if you just want an idea for what it looks like. But if you really want to draw a nice graph, we need to do better than that, right? And in that case, what we'll want to do is we'll want to use input-output tables to help us come up with an accurate graph. So this video is going to be about a very specific method for how we can generate a good input-output table for a complicated parent function. So there's a lot here, right? But in the end, in this problem, what I want us to do is I want us to graph this function, right? That's what I want us to have graphed, and I want us to have it graphed well, right? What we're going to do is we're going to do this in 3 separate tables. I'm going to start with the basic parent function. This function is clearly based off of x squared, so I'll start with a table of values that's just x squared. And this should be really fast. All I have to do is square each of these input values, right? So my outputs here will be 4, 1, 0, 1, and 4. Marvelous. Great, we've got that. This is kind of like in the previous video where we started with what the basic parabola looked like, right? In the next table, what we're going to do is we're going to take all of these outputs and we're going to stretch or compress them, right? In this case, because it's a 1/2, we're actually going to compress those things, right? So I'm going to take each of these outputs and I'm just going to multiply by 1/2, right? So that means the 4, 1/2 of 4 will be 2, right? 1/2 of 1 will be 1/2. 1/2 of this 0 value here will be 0. Again, 1/2 of 1 will be 1/2. And finally, 1/2 of 4 will give me 2. So I started with the original parent function. Then I applied my stretch or compression factor. And then the last thing I'm going to do, and this is probably the part that takes the largest amount of thought. The last thing I have to do is I have to apply the translation. So what is the translation, right? This plus 2 means that I'm translating left by 2, and this plus 1 on the end means that I'm translating up 1. That means that I need to change all of my x coordinates to the left by 2 and all of my y coordinates up by 1. So if I want to move my x coordinates to the left by 2, I need to take all of these x values and effectively subtract 2 from them. So my input values will be subtracted by 2. I'll have -4, -3, -2, -1, and 0. Okay? Then each of these outputs individually needs to have 1 added to it. So this 2, when I add 1, will become 3. This 1/2, when I add 1 to it, let's just call that 1.5. For the purposes of graphing, that's going to help us a lot. When I add 1 to 0, I'll end up with 1. Once again, when I add 1 to 1/2, I'll end up with 1.5. And finally, when I add 1 to this last 2 value, I'll end up with 3. And the idea is, this final table, if we carefully graph those 5 points, will give us a very nice sense, but rather not a very nice sense, a rather accurate graph of what our function looked like. So what we'll do now is we'll sort of use the graph that we have over here to plot those points and look at it, right? So if I graph -4, 3, and then -3, 1.5, and then -2, 1, then we have -1, 1.5, and finally 0, 3, this parabola that I'm drawing, you will hopefully notice this parabola is not as steep as the original one was. It has been compressed vertically, right? Further, it's been shifted to the left by 2 and up 1, right? So in the end, we get to the same thing. We get to a graph of these things, but the graph that we have is a lot more accurate than we had with the sketching method before. So I have another example for you guys. This is one that I'd like you guys to do on your own. The first thing we need to do is we need to figure out what's going to go in the top of these tables. And so I'd like you to pause the video for a minute and think, based on what we did in the previous example, what needs to go in the output of the first table? So just answer that question. What goes in the output of the first table? Well, the base function being used here is the absolute value function. So the absolute value of x is what needs to go here. Right? Now similarly, what's going to need to go in this second output? Like, what do I do with the second table? So again, pause the video, look back at your previous one, think about what's going to go there, and you know, what do we need to do as the output for this table? For this one, we effectively use the stretch factor. So in this case, I'm going to have -3 times the outputs from the previous table. This table feeds into this one by multiplying by -3, and then we apply our translations to get to the last one. So I'd like you guys to pause the video and sort of do these step by step. Complete the first table, then check it with the video, then complete the second table, check it with the video, then complete the third table and check it with the video. So the first table is just absolute value. I'll have 2, 1, 0, 1, and 2. Okay. So now, pause the video, come up with what the second table is. For the second table, I'm taking all of these output values and I'm multiplying by -3, by the stretch or compression factor. So now I am ending up with -6, -3, 0, -3, and -6. Okay, so now pause the video. Figure out what you're going to need to do with your translation factors and use those to create the third table for yourself. So the +3 means I'm shifting to the left by 3. The -1 means I'm shifting down 1. So that means all of my x coordinates shift to the left by 3. That means I subtract by 3. So I'm going to have -5, sorry, -5, -4, -3, -2, and -1. Then I have to take all of my output values and shift them down 1 unit. So if I'm shifting them down 1 unit, I'm subtracting 1 from them, I'll end up having -7, -4, -1, -4, and -7. This is the table that we need to graph. That's the thing that's going to give us the accurate picture of the absolute value graph that we're doing. So just like last time, we'll sort of shift sideways to the graph that I have here, and we'll plot these points, as many of them as we have anyway. We can't fit -7, -5, -7 on our graph. Like, we know it's, you know, sort of down here somewhere, but we can work with the rest of them. -4, -4 is here. -3, -1 is here. -2, -4 is here. And the same deal, -1, -7 doesn't fit on our graph. We'd have it down here somewhere. But fortunately, these 3 points are enough. We can tell that this graph is going to look like this. And I want you to notice a couple things. Notice first, this graph is, you know, opening downward. It makes sense because it has a negative coefficient. Second, this graph is steeper than the original one was. That makes sense because this was a vertical stretch. The absolute value of -3 is larger than 1. Finally, this graph has been shifted to the left by 3 and down 1. We can see that all of those components of the translations that we know about are happening. This is just a method that allows us to graph a little bit more accurately.